Hey, what is up guys? MKBHG here. Today we're going to solve move zeros, which is on LeetCode. We're going to use a two-pointed technique to perform in-place modification and solve this problem in constant space and linear time. Our comrade Robin will explain the theory and working of this algorithm, and then we'll code this together on LeetCode.
Since we are in two-pointer week, you know the drill. We are going to declare two pointers. In this case, the first one is called cur and the second one is called last non-zero. Now, cur is going to be moving from the 0th index all the way to the end of the array. And in case it encounters a non-zero element, then it's going to do a swapping operation. And the last non-zero pointer will always point to the index where the non-zero element can be added. Alright, so both of these are basically used for a swapping procedure. Now you can ask a question, how do we know when to swap? That's easy. We have to keep incrementing cur until it reaches the end of the array as explained. And now there'll be two cases. Let's say that cur points to 0. Okay, so if it points to an index where the element is 0, then you simply do nothing. You just increment cur. Whereas if cur points to an index which does not contain a 0, in that case we are going to swap the array elements of the two pointers, namely cur and last non-zero. After that is done, we are going to increment the last non-zero pointer. Okay, so let me show you a run through with the current example. So initially we are going to make both cur and last non-zero point to the 0th index. Now we can see that cur is pointing to an index which contains 0. So no swapping takes place. We increment cur. Now when we increment cur, we see that it's going to point to 1, which is a non-zero element. So what do? We swap 1 and 0 because that is where cur and last non-zero are currently pointing. So after swapping, we get an array 1 0 0 3 12. Now we know that every time swapping takes place, we need to increment the last non-zero pointer. So that too now points to 1. Next, we are going to increment cur. Now cur is pointing to 0. And what happens when we point to 0? We do nothing. So now we simply increment cur again. And now it's pointing to 3, which is a non-zero element. So swapping takes place. Now we are going to swap 0 and 3, which is the elements which last non-zero and cur are currently pointing to. So now we get 1 3 0 0 12. And what do we do next? We increment the last non-zero pointer. Easy, right? So what happens next? That's right, we increment cur and it's again pointing to a non-zero element. So we are going to swap 0 and 12, which is where the pointers are currently pointing to. And then we increment the last non-zero pointer. And now what happens? Cur has reached the last element of the array, which is the terminating condition. So this is the array which we are going to output. And that's really easy, right? Two pointers make everything really easy.
So now that you've heard and understood the core working of this algorithm, let's start the implementation. Step 1, we'll implement the logic. Robin used two pointers, current and last non-zero. These are two pointers that we'll be using. Our ultimate goal is to replace the last non-zero element with the non-zero element which we are currently encountering, and then move last non-zero towards right. Okay, so for each of the current element, that is here's the iteration which will step through each of the elements of num. Now we need the second pointer, which will point to the 0th index. Now, if the current element is not 0, then last non-zero element will be replaced by current element. In fact, it will be swapped. Now we'll move the last non-zero element one step ahead. Step 2. There is a lot of edge cases here. It's very straightforward. So with this, we are done. Let's see if it passes. And if we need step 3, that is debugging at all. As you can see, it's quite fast because we are using two-pointer method to do in-place modification. The time complexity of this is just one single loop that steps through the array one at a time. Hence, it has linear time complexity, and the only space that we are using is one extra pointer, which space is considered to be constant. So that is time complexity. Step 4. Optimization. In real-life environments, the variable name and documentation is very important, but in competitive coding environments, the typing speed is much more important. Hence, we're going to rename a couple of variables so you can type them fast. As long as you understand what those variables mean and you can explain it, then you're very well good to go. We're going to replace current with I and also last non-zero with j. These are common variable names that we use in Python to name iterable variables. That is, these are which are used in for loops as I. As you can see, it still is functional. There is one more update that we can do here. We can use post increment, which is the same as this. That is, first it will read nums of j, and once that read is complete, it will update j to the next value, that is j++. So this way you can remove these brackets too, and also these brackets. Doesn't that look a lot cleaner? What if I said there is one more optimization that you can do? Modern C++ provides an range-based iterators, as I've discussed in the STL video. Here we are going to take a reference of I for nums of j, for nums, which is here I will be taken by reference. That is, whatever modifications you perform to I will also reflect to the value which is present in nums, the array that is. Okay, so to code it something like this, if I is not 0, then swap and I. This is how small you can make the code if you use the right terms, right features, and right syntax. I hope you had fun. Subscribe to our channel and share with your friends if you had fun too. Bye. This is Vignesh. Ending was horrible.